Hi everyone, welcome to the 9th lecture of this second module on the course on measurement and instrumentation, and we are discussing about analog meters. In the previous class we have discussed about analog tool which is used to measure current, and today we are going to discuss about another kind of tool which you can use for measuring voltage across a circuit or across a resistance or maybe say capacitance. Okay. So, along with the voltmeter we will also see a basic ohm meter, that how it can be used for measurement of resistance, and of course we will have a separate section in this course where we will talk about measurement of resistance in different ranges, starting from say small resistance value, medium resistance value and high resistance values. Okay. So, let us start our discussion with the voltmeter today. As the name suggests, a voltmeter is an instrument which is used to measure the voltage or say potential difference between 2 points in a electrical circuit or say in a electronic circuit. Okay. It can measure potential difference in several kind of circuits, be it DC circuit, be it AC circuit. It can be utilized even for RF application also. These meters are relevant. Okay, and they can be designed based on the frequency range of the RF. Okay. If I talk about ideal voltmeter, it has a infinite resistance. Please you can correlate it with the ammeter that we have seen in the previous class, where we have seen that ideal ammeter should actually have a zero resistance basically. Okay, and the origin of that zero resistance was how it is connected in a circuit. Okay. Similarly, the origin of this idea that how ideal voltmeter should have infinite resistance, the origin of this is also very similar, like how it is connected in a circuit. Okay. So, when I say that ideal voltmeter has infinite resistance, basically it does not draw any current from a circuit. Okay. And by not drawing any current from the circuit, it does not affect the voltage which is under measurement. Okay. Real voltmeter has very high but finite resistance. It cannot be infinity. Okay. So, it draws basically a small amount of current. You cannot say that it does not draw any current. Okay. And this small amount of current which this voltmeter draws from a circuit can slightly alter the true voltage across the measured component. Okay. So, if I say let us take the same example where you have this voltage source, okay, and different resistances, say V, R1, R2, say for example say this is, I am calling it say R3, this is one node for example, and say this is R4. Okay. Now, say I want to measure the voltage dropped across say this R2, okay, or say another resistance, say I am calling it say load resistance RL, say if I want to find a voltage across this resistance RL. Okay. Depending on which element or across which element I want to find the voltage, I will connect my voltmeter. All right. Or say if I talk about in general a circuit, okay, depending on across what we want to, across which point I want to measure the voltage or potential difference, I will connect the voltmeters. Say these 2 points are say A and B point. Okay. And if I want to measure the voltage across this, I will connect a voltmeter somewhere here, and it is represented simply by a letter V which is encircled, and this will simply show a voltmeter which is connected across this circuit. Okay. So, this voltmeter that I have just now connected has very high resistance, but that high is finite, it is not infinite. Okay. Only the ideal voltmeter will have a infinite resistance. Okay. Now, when I say it has a resistance, means now the connection is along with this voltmeter there is a resistance element also, okay, and when there is a resistance element there of course it will draw a certain amount of current, okay, and this current drawing from this circuit can of course alter the true voltage which it would have measured if it would have not drawn any current from the circuit, okay. A voltmeter, as we have seen in case of ammeter also, operates on the similar principle on the electromagnetic deflection principle with a moving coil placed in a magnetic field. Particularly if I talk about the tools which we will be using for the development of these voltmeters, like say PMMC tool or moving iron tool and say electrodynamic tools. There are other tools like electrostatic tools which are electrostatic indicating instrument, of course, which cannot be utilized for the current measurement and are exclusively reserved for the voltmeters because of their structure and how they measure the voltage, okay. So there can be a variation in that, but in general a voltmeter operates on the electromagnetic deflection principle with a moving coil which is placed in a field will produce a deflecting torque which causes the pointer deflection proportional to the applied voltage, okay. This we have seen across all the instruments that we have discussed, okay. In a voltmeter the deflecting torque which is caused by the current through the coil is opposed by restoring torque from the control springs, okay, and the pointer reaches a steady position when these torques are equal and opposite. So control torque say tau c is equal to the deflecting torque at this position, we can say that the pointer has reached a steady state position or vice versa, okay. The final deflection of the pointer corresponds to the amount of voltage which amount of actually current now which is flowing through the current, and this current in turns is proportional to the applied voltage across the voltmeter terminals, okay. You can very similar to what we have seen for the ammeters, you can also convert a galvanometer to a voltmeter. We have already seen that how a galvanometer can be converted to a current measuring device or say ammeter. We have seen that this galvanometer can be utilized for measuring both current and voltage. Of course, we will discuss about this galvanometer in our next lecture, okay, but the basic idea of galvanometer is all of us are aware of, okay. In a voltmeter, similar to what we have seen for all kind of moving instrument, a rectangular moving coil is mounted on a lightweight frame and placed between permanent magnetic poles, okay. When a voltage is applied across the voltmeter terminals, a small current flows through the coil that we have just seen, which generates a deflecting torque which is proportional to the applied voltage, and because of this the pointer moves. This was the basic construction of voltmeter or say the voltage measuring tool that we have just seen, okay. This is of course homogeneous across all the instrument that we have seen, particularly for the permanent type of instruments, okay. The galvanometer can be modified as I have mentioned. A high value resistance which is known as a multiplier resistance Rm is connected in series with a galvanometer coil for conversion of this galvanometer into a voltmeter, okay. The purpose of this series resistor or the multiplier is to limit the current which is flowing through the galvanometer when a voltage is applied across the instrument, okay. Now because of this series resistance which is of course very high, the total resistance of the galvanometer and the series resistor is actually higher than that of if you take galvanometer alone, okay. An ideal voltmeter, as I have mentioned, is designed to have infinite resistance, ensuring that it does not draw current from the circuit and therefore does not affect the voltage which is being measured when connected in parallel, okay. The pointer and the scale of this voltmeter is very simple. The pointer is attached to the moving coil and this pointer moves over a calibrated scale which is marked in voltage, okay. Depending on what kind of voltmeter it is, the scale varies. the deflection of the pointer indicates the magnitude of the potential difference across the voltmeter terminals. Okay, the hair springs, very similar to what we have seen in the ammeter, provide the restoring or controlling torque which brings the pointer back to its zero position when there is no voltage applied across the voltmeter, and the deflection of the pointer indicates the magnitude of the voltage which is applied across the circuit. Okay, now there are certain points to be noted regarding how these voltmeters are connected. Okay, so as I have mentioned that the voltmeter should have high internal resistance, therefore they are mostly connected in parallel so that it draws minimal current. Okay, so for example, if I wanted to measure a voltage across this resistance R2 in this simple circuit, okay, I will not connect like a ammeter that we have seen in series. What I will do is I will connect it in parallel to the resistance R2. Okay, because of this it will actually, what current will do is, say for example in this circuit, if you say this voltmeter as I have mentioned has very high resistance. Okay, so this is a high resistance element. Okay, when I say high resistance means RV is much higher as compared to this load resistance across which it is connected, and because of this voltage source there is a current flowing in this circuit. Okay, the current will of course will try to flow through the minimal resistance path, and that's why maximum of the current is flowing through this R2, and that's how the potential difference between this point A and B is calculated by this voltmeter. Okay, since this has very high resistance, so now if say the total current flowing is say I, say this is I, this will be say I1, and say this is I2, this I1 will be much larger as compared to the value of I2. All right, so this I1 is much larger as compared to the value I2. So because of the high resistance of this voltmeter, it is not drawing any current, or even if it is drawing, the current is very low or very small. Okay, and because of this it does not alter the circuit voltage which is being measured. Okay, and the exact voltage from between this, or the potential difference between this point A and B can be calculated. Okay, the voltmeter should consume very little power to ensure accurate voltage measurement without causing any significant energy loss in the circuit. Okay, a voltmeter, as I have already mentioned, is always connected in parallel with the component to be measured to measure the potential difference across that component. Okay, it is designed with very high internal resistance to ensure that almost no current flows through the voltmeter, and the combination of parallel connection and high resistance allow the voltmeter to provide a precise and reliable indication of true voltage across the component. Okay, now let's talk about power loss in voltmeter. We have also talked about power loss in ammeter previously. The power loss in voltmeter can be given simply by V square by RV, where V is the measured voltage that it is measuring across this R2, and RV is the voltmeter's internal resistance. Okay, since a voltmeter has very high internal resistance, the current and power loss in voltmeters are minimal, ensuring accurate measurement without affecting the circuit's operation. Okay, the series resistance limits the current passing through the galvanometer. If I connect it this multiplier across this galvanometer, this is how we have converted. Okay, this has actually protected this meter from very high voltage across this meter if it get surges. Okay, and that's how these instruments are saved. Okay, in AC circuits, how it works is a voltmeter shows basically the RMS value of the voltage, not the instantaneous value of the voltage. Okay, it's very similar to what we have seen for the ammeters. Okay, say a sinusoidal voltage, say Vt is equal to V max into sine omega t. The instantaneous value of this AC voltage continuously varies with time and cannot be measured directly by any indicating tool, and that's why the RMS voltage helps us Okay, and similar, say for sinusoidal voltage, like what we have just seen, this Vrms can be given as, say, Vmax by under root 2, right? So the RMS value of the voltage is used because it represents the effective value of AC voltage, that is the value of the DC voltage which would produce the same heating effect in a given resistance. Okay, since electrical power and heating effect in a circuit depends on the square of the voltage, the RMS value provides a true measure of the voltage practical effect. Okay, and in the DC circuit, the voltage remain constant, and that's why the actual value, or say RMS value, or the average value are same. Okay, and the voltmeter shows a true voltage directly by which depends directly on Ohm's law. Okay, now heat produced by current in a resistor is, we have already seen, is V square into T by the internal resistance of the voltmeter, which is RV. Now this Vrms actually we have already seen is the effective DC value of an AC voltage because it produces the same heating effect in a resistor. All right. So say suppose say Vmax is 10 volt, Vrms can be written as, say for the sinusoidal wave that we have just seen, as 10 by root 2 or 7.07 volt. So we can say that a DC voltage of 7.07 volt gives the same heating effect as an AC voltage with the 10 volt peak value. Okay. Now this is how a voltmeter and ammeters are designed or connected in a circuit, and how they work when they connected is what we have just now discussed. Of course, we have not seen that how a PMMC tool, or say electrodynamometer, or a say moving iron tool can be converted into say voltmeter or ammeter. That of course we will discuss, because that is the most crucial part of this course, and that will be our major discussion across this course. However, what we are trying to do now is trying to understand that how this ammeter or voltmeter basically works. Okay. So coming back to the next meter, which is ohm meter. Ohm meter, as the name suggests, ohm, you know that it's a unit of resistance, and that's how ohm meter are designed to measure the resistance of a, say, metal or a semiconductor or any other resistive element. Okay. So an ohm meter, as I have just mentioned, is an electrical measuring instrument which is used to measure the electrical resistance by applying a known internal voltage to the unknown resistance and measuring the resulting current. So basically what you are trying to do is, you are having known internal voltage source. So you will find that all this ohm meter will have already internal voltage source, very similar to what we have seen in the potentiometer. Okay, so you have a internal voltage source, and unknown resistance is measured by measuring the current itself. Okay, so the current flowing through it, and by using a simple Ohm's law, you can calculate the resistance. Okay, the scale of this ohm meters is of course non-linear, and they are calibrated directly in ohms. Okay, we will also see that maybe in the later half of this course, that say a simple ammeter, for example, as I have just mentioned, that what you are trying to do is, you know the internal voltage, and you are trying to measure the unknown resistance by measuring the resulting current. Okay, so say you have voltage applied. Okay, there is a resistance. Okay, say you want to measure this unknown resistance, say I am calling this Rx. Okay, now the current flowing is, say, I. Okay, say if in place of this ohm meter, if it would have been a ammeter, and if in place of measuring resistance, if I would have been measuring this current, the scale would be like this for say ammeter. Okay, so this is, say, 0 amp. You increase is, say this is 2 amp, 3 amp, say 5 amp, say 6 amp, and so on. Okay, now say this is the measuring current, I equal to say V by R. Okay, now R is equal to V by I. Okay, means that, say, if the current flowing is very, very low. Okay, say there is no current flowing. Again, I will draw this circuit. in place of say ohm meter, I have connected a ammeter, okay, and the ammeter is showing that there is no current flowing in the circuit. It means that there is no Rx, or it's simply a open circuit. So I will just delete this part, okay. So it will show that simply that it is a open circuit, okay, and the resistance is say infinite, right. So on this scale, if I want to say, if I just remove this and say I want to, on top of it I want to plot say scale to show the resistance, okay, what I will have is, I will have say this R equal to infinite, okay. Now say it will decrease, okay, and say at some point say this current is very very high, okay, right. So means that in this circuit all the current which is say it has multiple resistances, for example, okay, means all this current is flowing through this, means it is a short circuit, right, means that this resistance is 0, right. So now in the second case I have this resistance, say there is no resistance, for example, all right. So this scale, if you see, it has a very unique point, like here this R is infinite and here R is 0, okay. So for the ammeter, if you see, the scale is from this left hand side to this right hand side, and here it is just opposite, like from 0 to infinite, okay. So a constant internal voltage source is used, as I have just mentioned, okay, means that if the resistance is high, the current will be small, okay, we have just seen, right. So you have this voltage fixed, very fixed voltage, okay. Now say the resistance which is under measurement is very very high, okay, this R is very very high, means that the current value say that it is measuring will be very small, okay. And if the resistance is very low, okay, or say there is no resistance, basically just it is just wire, means whole of the current is flowing, means this current is very very large, right. So of course it's a relative discussion, okay. So you have this Ix as say very high, okay. Now the meter deflection is, which is basically because of the current, is then mapped to the resistance, very similar to what we have seen, okay. So if I have to construct a ohm meter, it will have several essential things, like you have a DC source which is a fixed source, then measuring movement which is like a PMMC meter and other things, we'll see that, okay. Then you have current limiting resistor that you require to protect the meter and set the current range. You have 0 ohm adjust control to compensate the battery aging and the temperature effects, and you have test terminals or probes, which is the point where the unknown resistance is basically connected, okay. So basically these ohm meters are of two different type. One is the series type ohm meter, and then we also have a shunt type ohm meters, okay. Just have a look on this series type ohm meter. This is a series type ohm meter, okay, and if you see it carefully, the measuring resistance, which is the unknown resistance, is connected in series with the meter. This meter is say basic meter, say this can be a galvanometer, okay. Now the value of resistance is measured through this meter, which is connected in parallel with the another shunt resistor, this R2, which is a variable resistor, and this is the fixed battery source that I was talking about. So this is a basic construction of a series type ohm meter. We will of course discuss this measurement of resistance in more detail later on, but this is just for description or just for the introduction that how this ohm meters looks like, okay. The parallel resistance R2, this is known as the parallel resistance. This is connected in another resistance which is known as the series resistance, and this is the R1, which is the adjustable resistor, okay, and this is also connected with the battery. The component whose resistor is to be measured is inserted into this probe between point A and B, okay, and the unknown resistance is connected in parallel with the meter in case of the shunt type ohm meter. Okay, in the series type you have just seen that the measurement is something like this. So you have this unknown resistance connected across this pin and is connected with series with the basic meter. However, in the shunt type ohm meter it is just connected across parallel. However, if you see, there is another important point to see, that there is a switch over here which was not present in case of the series kind of ohm meter, and this is just to avoid always connection of battery, to avoid the drainage of this battery, and at different point you have different deflection. Will not go into those discussion, because as I have just mentioned that we have to take this resistance meter in more detail in our upcoming classes. Okay, so please note that this connections of unknown resistor and basic meter or the galvanometer is very crucial, and based on this only you can distinguish between two different ohm meters, okay, be it series or be it shunt kind of ohm meter. Okay, if I have to compare different parameters between these two series and shunt ohm meters, you can see that the unknown resistance is connected in series with the meter and the battery we have just seen, okay, and in the shunt it is connected in parallel with the meter. The basic meter has the battery, meter, series resistance, etc., while for the shunt it is the battery, meter with the which is the shunting with the meter. Okay, the operating principle is like increasing in the Rx value decreases the current, while it is just opposite in the shunt ohm meter. Decreasing in the unknown value will decrease the meter current depending on how it is connected. Okay, now deflection at Rx equal to 0 is basically a full scale deflection or the maximum deflection in case of series ohm meter, while it is just opposite in case of shunt ohm meter, and that's why the scale of the series ohm meter and shunt ohm meters are just opposite. So the scale that we were just talking about, like R is infinite this side and R is 0 this side, okay, this kind of scale is followed by the series ohm meters, while for the shunt it is normal like any other meter, like R 0 is here and R infinite is this side. Alright, so the maximum deflection is at Rx equal to 0 in case of series ohm meter because of their connection, okay, and at Rx equal to infinite, series ohm meter will have 0 deflection, while the shunt ohm meters will have a full scale deflection. Okay, the scale nature in both the case are of course non-linear. However, the scale, as I have just mentioned, in the series ohm meter is the reversed scale, while in the case of the shunt ohm meter it is the direct scale that we utilize. Okay, so this is in brief about different meters, different ammeters, voltmeters and ohm meters. Okay, now once we have understood these meters, how this PMMC or moving oil or electrodynamometers can be utilized as a ammeter or voltmeter or their combination for the resistance meters or resistance measurement, be it high, be it low, or be medium kind of resistance, will be much easier for understanding. Okay, so we will be talking about galvanometer in our next class, and in the next week we will start our discussion on different analog meters like PMMC, moving iron and so on. Thank you.